Welcome to Why Festo Electric Drives, a series of short videos explaining and showcasing some of the most unique features of the Festo CMMT servo and stepper drive family. Today we will be showing how easy it is to optimize a system's tuning using simple closed-loop tuning settings in combination with the trace configuration in Festo Automation Suite. Let's get started. As you can see, this system is powered by a Festo power supply and includes a CMMT stepper drive, EMMS stepper motor, 2.5 meter motor and encoder cables, and an ELGC ball screw linear actuator. Transferring over to Festo Automation Suite, we can see that the first setup is already completed. I will check that the application mass of 0.039 kilograms is correct on the Application Data tab. There, you can see the application mass is correct at 0.0393 kilograms, just like in our sizing report. Second, I will utilize the recommendations in the Electric Motion Sizing Report downloaded from the online EMS tool to set up 3 records with transitions in the record table. We will move from 0 millimeters to 100 millimeters to 190 millimeters and return to 0 millimeters with the velocity, acceleration, deceleration, jerk, and inning velocities shown in the sizing report, as you can see here. Here you can see I have those same 3 positions, extending to 100 millimeters, extending to my full end of stroke, 195 in this case, and then retracting to 0, and all 3 of those occur in sequence. Third, I will set up a trace to record the path and the position control error of each closed-loop tuning setting during testing. Because the position control error is the difference between the planned path and the executed path. Here you can see I'll be recording the set point position, the actual position, and then on channel 6, the position control error. I'll be recording for a duration of 4.25 seconds. And as soon as the velocity is greater than a 0 value, here 2 micrometers per second, I will start my trace. Now I will set up my screen so that I can see everything I need for trace and tuning. Now I'm ready to begin my testing. As you can see here from the Parameterization tab, Axis 1, Closed Loop Tuning section, you can see under Closed Loop Calculation that I have my slider set for the middle position. I'll press Calculate and store those parameters. This will be our first of 5 standard positions: middle, middle soft, soft, middle hard, and hard that we're going to test. Now that my closed loop calculation has completed for the middle position, I'll store it on the device. Now I'll return to the Diagnosis tab, click on Trace Display. You can see I have no traces currently to display. I'll pull my plug-in control, acknowledge the pop-up, enable my power stage or my load power, start my trace, and start my first record of 3 and wait for it to complete. I get a pop-up that a new trace result is available once the motion is complete, and I can see that it's recorded those specific positions. If I zoom in on the position control error, I can see during the standard motion, I have an approximate maximum error value of 0.00503 millimeters. Now, when I get to the end of stroke, I can see that there's another maximum position control error that occurs due to the deceleration. If I zoom in on that, I can see that that value is approximately 0.028 4967 millimeters. So we have two metrics for position control error, one during the standard motion and one that occurs during acceleration or deceleration at the ends of path. I'll record those two values, rename the trace, and now I'll repeat the process by going back to the Parameterization tab, disabling my power stage and plug-in control, moving the slider to the soft middle position, pressing calculate, waiting for the closed loop parameters to recalculate, and then storing on the device. Once my new parameters for the soft middle position are stored on the device, I'll return to the Diagnosis tab, start my trace, enable my plug-in control, load power, and start the motion again for this second position. I'll repeat this process of analysis until I have standard position control error values for the middle of motion and maximum position control error values for the ends of motion until I've analyzed all 5 positions. Now that I have traces recorded for all 5 positions on the closed loop calculating slider, and I've pulled values for the standard position control error and maximum position control error when accelerating and decelerating, I can see very clearly that out of those 5 settings, the soft position on the slider, or the far left, produces the most minimized standard error and max error by several micron. Lastly, I will return to the soft closed loop tuning settings. I'll go to the Parameterization tab, Axis 1, Closed Loop, disable my power stage and plug-in control, put my slider in the soft position, calculate, and lastly store on the device. For most single-axis systems, these 5 closed-loop calculation slider settings are more than enough to create a stable linear actuator with the most minimized position control error. If these standard settings don't reduce the position control error enough across the entire path for your application, there are additional advanced settings for tuning the system further. Look how quickly we got started. Stay tuned for additional videos on why you should consider Festo electric drives.